Welcome everybody. This is Adam from PCWorld with Dr. Ian Cutress from TechTechPotato. You were recently at Hot Chips and you saw a talk about a new technology that I think we're going to find kind of interesting, at least on the consumer side, but it applies to more things, but we're going to talk about it specifically on liquid coolers. So there's a technology in here, it's a copper plate that wicks away the heat to try to get the most efficient cooling possible. You saw a technology from a company that's a startup that has a different design of the copper that's underneath this plate, right? I guess first describe better than I just did how it actually wicks away the heat.
So this sort of water block, you have obviously fluid in, fluid out, and then as the fluid moves through from one end to the other, you need to have as much surface area as you can, because that then conducts the heat away from essentially the hot part, which is connected to your CPU.
And it's usually like fins, right?
Yeah. Well, yeah. So you have that conductance usually as horizontal fins, and then you have the flow of the liquid is the convective element.
Okay.
Right. So you can move the heat away quickly. And most designers like this use straightforward fins because it provides a nice balance between having that surface area and having that fluid flow. It's also really easy to manufacture.
Oh, I can imagine.
As you imagine, completely straight. Sometimes you'll see some that are slightly bent or slightly curved, and you realize that what they're trying to do is they're trying to slightly increase the surface area, but keep the flow consistent.
Okay.
Now, this presentation at Hot Chips is taking a proper mathematical view at what is the combination of the best surface area combined with the best fluid flow to get the best cooling performance out of what would be a standard liquid block.
So the way you described it to me is that you want to have more surface area because you want to have more liquid touching that surface to wick away the heat, right?
Yes, yeah.
But you also, it's a volume play as well because you need to actually get the fluid through there.
Yeah. If you could increase the surface area, massively, but if you can't push the fluid through at a good rate, then the heat is going to stay in the fluid, and you're not going to be able to get it away. So it's this mix of conductive and convective elements inside the block that matters the most.
So this company, what's the name of the company? What's the name of the product? And what's their solution then?
So the company is called Fabricate. That's fabric with the letter 8 because
Oh. Okay.
We are in this generation right now.
I get it.
And they've essentially done the mathematical models to try and find what is the best way, what they think is the best way to combine these convective, conductive elements. And then by using essentially 3D printing methods, so they call it ECAM. Okay. Electrochemical additive manufacturing. So what you have is essentially, kind of think more like resin printing and the whole laser printing, where you have this conductive essentially fluid and you're depositing micro copper and growing up a structure from a base, right?
Oh, okay.
So that allows you, depending on your accuracy and depending on what materials you use, to have a finer control of how thin the fins are, also how rough the surface is. Because there's this concept in fluid dynamics called laminar flow and turbulent flow. So you want to minimize turbulence, so you actually get better flow rates. And what they've done is they've applied this essentially modern fluid dynamics model and optimize it for fluid flow into a liquid block, into a closed loop liquid cooler. So we were debating before this video whether we should actually take this off to show. I'm sure we can find pictures to put up.
Yeah, I'll just use a photo.
Yeah, because this is still full, and we didn't really want to put ethylene glycol. It's not always water in these; it's usually some sort of oil, and oil is obviously viscous. So you're trying to get the right amount of viscosity in your fluid as well.
Okay, so this company had two different things to show off, right? Two different patterns or manufacturing, or I don't know how to describe it. They call it structures, I guess that's the word they're calling it. So walk me through the two different ones they're showing.
So the structure they've generated, they've called it a gyroid, which imagine you've got like Swiss cheese. Right, but you've got regular holes in the Swiss cheese going all the way through.
Okay.
and then you apply a twist to the design.
Oh.
I'm pretty sure looking at the picture you can kind of see that, right?
I see that.
There's
just a lot of holes.
Yeah, it's twisted Swiss cheese.
Okay.
And the point of, by adding the curvature and by regulating the size of the holes, you can essentially get something that performs similar to the standard microchannel design, that sort of really thin fins, or you can get something that actually acts a lot better because you're adjusting for surface area, you're adjusting for what is the open volume, you're adjusting for fluid flow. And so you can actually get the right combination of those two variables to maximize your cooling. And we can actually show a picture of what these look like because they had a couple to show off. They kind of look almost brittle.
Yeah, that was going to be my question. Is it seems like with the traditional kind of stack, it feels like that would be kind of have more tension than this, but
yeah.
I mean, that's probably wrong from a mathematical standpoint, right?
I think they said they able to do an accuracy of about 20 or 50 microns, but the wall thickness of this is about 100 microns.
Okay.
Which is kind of in line actually with what fins look like inside here, right?
Okay.
With other chemical processes. Now, what this means is you can essentially reduce your pump rate to get the same cooling performance, and so save power. One of the big arguments here is so much power in data centers, right, is actually just the heat generation and the heat removal. So if you can find a way to make that more efficient, then this is one such solution.
But it would benefit gamers as well.
So another thing is, it turns out this process is incredibly cheap.
Like cheaper than traditional methods?
Cheaper than traditional methods. Between different additive manufacturing technologies, it's the cheapest around.
Wow, okay.
Compared to the standard curing, powdering, sintering of what would be standard microchannels, other additive methods. I can show you here, there's a big $1 sign rather than the $3 sign.
Okay, that looks cheaper to me on this chart at least.
Yeah.
But okay, so if it's cheap and it's better, how come nobody's done it yet?
That's what I'm wondering.
Oh, okay.
And I think part of it is this electrochemical additive manufacturing. It's a known process, but I don't think anybody's really applied it to this sort of topic before. Because the way of doing fins just feels so naturally the right way of doing it.
Yeah.
I mean, you look at this gyroidal structure and you think, wait, that's better? The first thing I thought was, hey, is that going to be better than fins? One good thing here, though, is that fins are universal. Everybody's regular with fins. Now, a modern CPU has hotspots, right? There are bits that heat up better, there are bits that heat up not as much because it's just standard logic or what have you. With this additive method, this electrochemical additive manufacturing method, you can actually optimize your heat sink based on, or optimize the block in here for specifically where the heat is generated on the processor.
Wait, optimize how?
As in, you change the nature of the structure based on whether you want flow.
Oh, wow.
Or for costs.
Huh.
Or you can actually have different structures at different parts of your additive manufacturing.
Oh.
And as long as the flow all works out around it, you can get better performance out of your chip.
Yeah, because it's like with the new Ryzen 7000s, we're seeing the offset of some coolers because they're like, hey, it's hotter, on one side than the other.
Yeah.
So this is kind of that same thing where you could actually build the structure to address the hottest part of the chip.
Yeah. It does. It would mean making sure that you actually mount it the right way.
Well, yeah. Read the manual.
Read the manual.
Read the manual. Yeah.
Don't leave the plastic thing on like I did once.
Ooh.
Yeah. That was a fun review.
Yeah. So when we're talking about fins, I mean, the other part of it is that it's that same kind of thing here too. You got fins. You're trying to get air through it. Does the same thing apply for air versus liquid?
So air is typically called a fluid. So you could argue yes. The downside here, so for the block, you've got solid fins, or solid, these sort of gyroidal structures, and then the fluid is flowing around it. Part of what you have to think about here is also the fluid inside the fins and where that transfer is going into. So it may be a little bit more complicated.
Oh, okay.
Because you have to design that structure to have some flow inside it. Right? So, yeah, it's... I think this is the cheaper one right now.
Okay.
And also, this is this is copper, right? If we apply it to aluminium, there are different different considerations in play.
Well, but the same copper plate is on tower coolers, so we can see it there as well. So
yeah, there's been some talk about whether this could be applied to air cooling. You know, you still have your standard heat pipes, but maybe the fin structure around it is a bit more, you know, it looks convoluted, but actually the performance is better if you have the right amount of flow. That being said, how many times have you cut yourself on a tower cooler?
Oh, all the time. Yeah.
I think if it looked like this structure, that'd happen a lot more.
Oh, yeah. And that doesn't look like clean cut either.
No. Emergency room, maybe.
Huh. Interesting. Okay, well, yeah. Do you... So this is a startup. I mean, are these in any products right now? How close do you think we are to seeing an actual product you can buy on the shelf?
Part of the issue is very similar to when you've done your detail on Floor Labs. Right?
Oh, yeah.
Right,
okay.
they have a new air cooling product, but they're going up against a highly commoditized, high volume, low margin market. So they're going to come across a lot of the same issues that Floor have. So
interesting.
It's
so it might take some time, but it seems cheaper, more efficient, easier to make.
Well, so what I can see is that, you know, there are like 2 or 3 major closed liquid cool manufacturers in the market today. You know, there's the whole patent thing that went on. If one of them picked it up and licensed the technology and was able to put it in mass, and then that was the turnkey solution for everybody else to use, then yeah, we could see it coming. So
it might just all of a sudden be in all of them.
Yeah, and whether they market it or not, we may not know.
Oh, true. Yeah, we'd have to take it apart.
or if something goes wrong and you have to start cleaning it, right?
Yeah, right.
Actually, it's easier to clean fins.
Why?
Because
easier to clean fins. Yeah, because just straight through. Yeah.
So if you do get a build-up,
yeah, huh?
We'll see.
Interesting.
They didn't go into that detail. Like I say, they showed off some of the. They didn't show off any units that were kind of already put together.
Oh,
it was just the little copper blocks. So,
huh? Interesting. Okay, well, we'll keep a look on that. I guess every time you buy a new one, maybe just open it up ahead of time and just check to see if it's got the new one in it. No? Oh, okay. Well, let somebody else do that. Let somebody else do that. Yeah. Until then, thank you for this amazing report, Ian. I had no idea until you were like, "Hey, we should talk about this." So. Now I know, and now you know. So now you can thank Ian. So, and I'm going to thank you for watching. If you want to find out more interesting things like this new cooling technology, subscribe over on Ian's channel, because that's where the interesting stuff happening. But, you know, if you want to subscribe to us, you can do that as well. Until then, we will see you in the next video. Thanks, Ian, for stopping by. Thank you for watching. We'll see you later.
You can also blame me.
Oh, I could blame you. If it doesn't take off, we blame Ian.